Hello everyone. I welcome you to this class of econometric methods. Myself, Dr. Muhammad Imdadul Haq, an associate professor at the Department of Economics, Aligarh Muslim University. Today's lecture is on the topic of Johansen Cointegration. We had our discussions on cointegration, and also we have seen the process of Engel-Granger method of cointegration. So, what basically is cointegration? It's long run relationship. So, if the series under examination are integrated of the same order I1 and there is a linear combination of the series that produces and stationary series then the series is said to be, then those two series are said to be cointegrated. It is quite possible that two I1 series or two series having a stochastic trend do share a similar common trend, so that the regression of one on the other will not be necessarily spurious. So, a quick recap of the process of Engel-Granger. So, we have two non-stationary series. If we do simple OLS regression, the results would be spurious. Now, and there is a rule of integrated series which says that if two series are I1 and any linear combination of them will also be I1. A linear combination like that, we say we have two series YT and XT and they are I1, and we have a linear combination that is ET is equal to YT minus beta 1 minus beta 2 XT. Now, if according to the properties of integrated series, this series of ET, it should also be I1. But as a special case, if somehow this series is I0, a combination series is I0, then we can say that there is a long run relationship between these two variables. So basically this Engel-Granger method was a test of stationarity of the residual. If the residual series is stationary, there is cointegration. If the residual series is not stationary, there is no cointegration. Now, so cointegration implies that YT and XT share similar stochastic trend, and since the difference term ET is stationary, they never diverge too far from each other. This series, this constructed series, this series which is made up of a combination of YT and XT, since it is I0 series, so it serves as a proxy of the power that drives the random walk and prohibits them to diverge from each other. But there were some issues with the Engel-Granger, and one of them is that if there are more than two variables, say now we have YT, XT and ZT, so there are three variables, then there may be more than one cointegrating relationship. One may be between say XT and YT, and the other may be between YT and ZT. In Engel-Granger, we do not know if there is one or more cointegrating relationship. So, but meaning thereby, if there are k variables, there can be k minus 1 cointegrating vectors. In such cases, we have to go for other test apart from Engel-Granger. Basically, Engel-Granger was a single equation framework. Now, we move on to the multiple equation framework. If you, this was the reason why we studied VAR before moving on to Johansen Cointegration. So, this is the model which is in front of you. The model in front of you is nothing but the same VAR model. where y1t is a function of past values of y and also past values of x plus the error term. Similarly, x is a function of past values of y and past values of x. So this is what we have, this is the model which we have studied while we were doing VAR, and this is nothing but a multiple equation framework. Now we will apply the concept of cointegration in a multiple equation framework. To do this Johansen cointegration, the first step is lag selection. See, if lag selection is not done properly and by any chance an important variable or important lag is omitted, then this omitted variable and this omitted lag variable will sit in the error term. And the moment it sits in the error term, then it will lead to many issues. The estimates will no longer be adequate. The estimates will no longer be correct. Through the help of eViews, we just have a quick look. So what we do, once we go for VAR specification, in order to estimate the lag, we go for VAR specification and then we select the standard VAR over here. We will be selecting this option. We will write all the variables x, y, z, and here it can be left as it is. At the moment it does not make much of an issue. So we have we simply insert this. This is the most common method. This is the most popular method to decide upon the optimal lag. In what we do, we go in the VAR framework and we take all the variables in a raw format. Means we are not taking any differences. You are just taking the raw data x, y, z over here. Now, once we have got the output of the VAR, which is of at such no use over here, then we move on to the lag structure, and in lag structure we will select the lag length criteria. Once this and this is all done in the VAR framework. So over here this result is what we are interested in. Now see, we have many criterias. Some of the popular criterias are Schwarz information criteria, Hanan-Koinen, and even a Kaike. These are some of the popular criterias, and there are other also criterias are there, but let us go by these three. Now, the software, very interestingly, it gives you the model with the best lag. It automatically tells you that these two criterias, that is Schwarz information criteria and Hanan-Koinen information criteria, says that we should take a lag of 1. Whereas there are certain criterias like AIC, it is saying that you should take lag 5. If you come across such a case, then based on the principle of parsimony, we will take the one with the smallest lag. Although two different criterias are suggesting two different lags, but we will take the one which is having the smallest lag term. So this is the process of lag selection. And say in each of these models, we inspect the values of AIC and SC criteria. In general, the model that minimizes AIC and SC is selected as the one with the optimal lag length, and then we have selected lag 1. So with this we completed our first step, wherein we were selecting the lags. In step 2, we have to select the appropriate model. There are so many models, approximately 1, 2, 3, 4 and 5. There are 5 models among which we have to select one. Now these 5 models are like, the first model is no deterministic trend no deterministic component in the data. Second model is no linear trend in the data. Third, no linear trend in the levels of the data. Model 4, there is trend. Model 5, this is the unrestricted model. So in model 1, this is, however, this is quite unlikely to occur in practice because we don't have a series which normally in economics we don't have a series with mean 0. This is something which is we don't have, but so this is very unlikely. Model 2, the first difference series will have a 0 mean. Model 3, now there is a drift around the intersect. Model 4, now there is a simple trend. And model 5 is again, this is unrestricted model, and this is very difficult to interpret from theoretical perspective. It implies an ever increasing or an ever decreasing phenomenon. So we restrict ourselves to basically model 2, 3 and 4, and that too for if you go by research papers, they prefer model 3 and 4 only. They prefer model 3 and 4 at most of the times. Now, according to the Pantula principle, model 1 and model 5 are ignored. Both model 5 is also very difficult and model 1 is something which is impractical. Now what we do, we proceed from the most restrictive model, which happens to be model 2, and then we go to the least restrictive model. Means first we take the model 2 and then we estimate the Johansen cointegration. Let us see, and then we take model 3 and then we estimate Johansen cointegration, and we can take model 4 and then estimate the other things related to Johansen cointegration. And then herein we compare the trace statistics, and then we select the first model which shows cointegration. So once the model has been selected, now we move to step 3. Here the presence of cointegration is ascertained with the help of the rank of a matrix. See, Johansen test uses this pi matrix in vector error correction model specification. This matrix is also called as the LR coefficient matrix, and basically the testing of the cointegration among y's is done by looking at the rank of this pi matrix through their eigenvalues or the trace statistics. Now this eigenvalue which we are referring to, or the trace statistics, this test statistics are based on the characteristic root or called eigenvalues obtained from the process. The test consists of ordering the largest eigenvalue in descending order and considering whether they are significantly different from 0 or not. Suppose we obtain the characteristic root denoted by say lambda 1, and lambda 1 is greater than lambda 2 and lambda 2 is greater than lambda 3 and extending up till lambda n. If the variables under examinations are not cointegrated, the rank of this pi matrix is 0 and all the characteristics will be equal to 0. Therefore, say 1 minus pi hat I will be equal to 1, and since ln I in the formula is equal to 0, each of the expression will be equal to 0 for no cointegration. On the other hand, if the rank is equal to 1, then the value of pi will be greater than 0 and less than 1. So that the first expression, that is 1 minus pi hat I, is less than 0, while all the rest will be equal to 0. So based on this max statistics, here we take a decision, we are able to decide whether there is a cointegrating relationship or not, and here the null hypothesis is there are R cointegrating vectors, and the H1, the alternate hypothesis is there are R plus 1 cointegrating vectors. Similarly, we also use the trace statistics. Here the null and alternate are said a bit differently. So H naught is at most R cointegrating vectors, and H1 there are more than R. And the alternate hypothesis is there are more than r cointegrating vectors. Now here we test the null hypothesis that the number of distinct cointegrating vector is less than or equal to r against a general hypothesis that it is more than r. The trace statistics, it considers whether the trace is increased by adding more eigenvalues beyond the rth term. The null hypothesis in this case is that the number of cointegrating vectors is less than or equal to r. From the previous analysis, it should be clear that when pi hat I is equal to 0, then the trace statistics is also equal to 0. On the other hand, the closer the characteristic root are to unity, the more negative is this term. So, because what we have seen earlier, if pi hat y is equal to 0, then the trace statistics is also equal to 0. On the other hand, the closer the characteristic root are to unity, the more negative is the value of ln 1 minus pi hat I term, and therefore the larger the trace statistics. We will take a simple example and it will be clear. So, through the software, if you want to see, it is very clearly here there is both the things, the trace and the maximum eigenvalue, the two tables that we are getting, and it gives a direct result is stated over here. The trace test indicates one cointegrating equations at 0.05 level. If there are more than one, suppose there are two cointegrating relationship, then here it will be the trace statistics indicate two cointegrating relationship. If there is no cointegration, then it will say trace statistics indicate zero cointegrating relationship. Similarly, the maximum eigen test also indicates one cointegrating equations at 0.05 level. So, basically what happens here, the test is conducted in a sequence, none or 0, then 1, then 2, and likewise it will increase. If say r is equal to 0 versus r is greater than 0 and less than g in trace statistics, and in max statistics r is equal to 1. Similarly, in r is equal to 1 versus r is greater than 1 and less than g in trace test, and r is equal to 2 in max statistics. And if the calculated test statistics is greater than the table value, we can reject the null that there are r cointegrating vectors, otherwise accept the null. So, we can go by checking the probability values, and from this we will get an understanding. Like see, from none it's less than 0.05, but since there is 1 after 1, it becomes more than 0.05. Similarly, in the maximum, when it is none, the probability value is less than 0.05, and once we have achieved 1, that is at most 1, then it becomes more than 0.05. So, mathematically, the rank of this pi matrix is equal to the number of non-zero eigenvalues. If rank of pi is equal to 0 and pi is equal to 0, that is a null matrix, and then there is no cointegration over there. If this rank is equal to full k, then all the variables are stationary and we can simply use var. And if rank is equal to m, given that m is less than k, then there are m non-zero eigenvalues, then there are m linearly independent cointegrating vectors. Once we have got an idea that there is a cointegrating relationship, then the next step is we go for vector error correction model. Now, this is the vector error correction model comes only after once Johansen cointegration max and trace statistics have been estimated. So before a specification and estimation of VCM, we initially have to use Johansen test and find out how many co-integrating factors are there. Now, suppose we have three variables y, x and z, and there is only one co-integrating relationship. Then what we do, we normalize with respect to any one variable, y it becomes 1, and we get the values for the others. So this equation is called as co-integrating equation. Now, in the next stage, we include the errors from this equation in the short run model, in which we have the equation dy, delta x and delta z. Now here, then we get these are the error correction terms. Now this error correction term, now it must satisfy few conditions. The first is it should be negative, and that is here. The error correction term value is minus 0.02. But if I go to the last value, this last value is T stat. Now this the calculated value of T statistics is minus 0.74. And if I go by the rule of thumb, any T stat value of less than 2, it means it will not be significant. So although my co-integrating error, or although my error correction term is negative, but it is not significant. And also, although here it is in case of delta y it is not significant, also in case of delta x it is not significant, but in case of delta z the value is minus 4.04, so it will be significant over here. A T statistics value of more than 2, it means it will be the null hypothesis will be accepted over there. It can be a case that here it is not significant, or here the T statistics is less, than 2, but in the last case our variable has become significant. So this can be the case, but we are mainly concerned over here with this the first equation, as although theoretically in co-integration there is no dependent and no independent variables, but we normalize and we estimate the equation in terms of one of them. So now on the right side of the equation we include the lag terms and error from the first stage co-integrating. So this is what you can say is your vector error correction model, and this is estimated through OLS. So we have the terms for zt minus 1, we have the terms for xt minus 1, and this is our error correction term, and this is what is our error correction term, and it should satisfy the condition of being negative and significant. So the ECT term should be negative and significant, and the coefficient associated with the error term are called as adjustment parameters. And also note that since the error term is included in the three equations, this term may be significant in all the cases, or it may be significant in one or two, but not significant in others. Now we go for a demonstration of the process. We have written those two equations. Yt is equal to alpha plus beta yt minus 1 plus gamma xt minus 1 plus epsilon 1, and the second equation is xt is equal to a plus theta yt minus 1 plus lambda xt minus 1 plus epsilon 2. These two equations can be written in the matrix form. This is written over here is the first matrix. This happens to be our second matrix. The plus sign comes here, and we are taking the coefficient matrix, and we have this yt minus 1, xt minus 1 plus epsilon 1 and epsilon 2. Next we take our very first equation of the model, and then we do a small bit of algebraic manipulation. We deduct from both the right hand side and the left hand side yt minus 1. So yt minus 1 is equal to alpha plus this common, then here beta yt minus 1 minus yt minus 1 plus gamma xt minus 1. From here we take yt minus 1 common, so we can write delta yt is equal to alpha plus bracket open beta minus 1 bracket close multiplied by yt minus 1 plus gamma xt minus 1. The same thing we do for the second equation, that is xt is equal to a plus theta yt minus 1 plus lambda xt minus 1 plus epsilon 2. Now we deduct xt minus 1 from both sides. So there is a small amount of correction, it should be xt minus 1. So xt minus 1 is equal to a plus theta yt minus 1 plus lambda xt minus 1 minus xt minus 1 plus epsilon 2. Now we can write this in the terms of delta xt is equal to a plus lambda plus theta yt minus 1. Here we take xt minus 1 common, so it is multiplied with lambda minus 1 plus epsilon 2. Now we have these two equations. These two equations we can write it again in the form of matrix. So once we have written it in the form of a matrix, as is evident, we have the first matrix yt minus 1 xt minus 1, then here it is lambda alpha a, and this coefficient matrix beta minus 1 gamma theta lambda minus 1, and then we have this yt minus 1 xt minus 1 plus epsilon 1 epsilon 2. So this we write it as simply as delta y and delta x matrix and a alpha a, and in place of beta minus 1 we denote it by r11, this is denoted by gamma is denoted by r12, theta is denoted by r21, and lambda minus 1 is denoted by r22. So we write it in this form and multiplied by yt minus 1 xt minus 1 plus epsilon 1 epsilon 2. Now here the rank of this matrix will be decided by the rank, the cointegration will be decided by the rank of this matrix. The rank of cointegration indicates how many linear combinations of the variables are stationary, implying a long run relationship. So what is matrix rank is equal to the number of linearly independent rows and columns. As a demonstration, we are having here three different matrices. So if two rows or columns are linearly independent, if it is not possible to express one of them as a multiple of the other. Now let us take the first matrix, matrix A. Here column 2 cannot be expressed as a multiple of column 1 or vice versa. So matrix A has two linearly independent rows. Matrix B. Here rank is equal to 1 because see row 1 is the column 2 is twice column 1. So column 1 and 2 are not linearly independent, and matrix B has only one linearly independent column, so the rank is equal to 1. The last matrix, it's a square matrix containing only zeros, so there are no independent columns, so the rank is equal to 0. So the same equation in the matrix format we have written, and this is my pi matrix which is deciding the rank of the matrix, and from where we are getting an idea of whether there is cointegration or not. So if y and x are I0, this rank of this pi matrix is equal to 2, indicating no cointegration. If yt and xt are I1 but an I0 combination exists, rank of this pi matrix is equal to 1. xt and yt are cointegrated. That is, the third case, if x and y are I1 and no I0 component exists, then the rank of a matrix pi here is equal to 0. We can say xt and yt are not co-integrated. So basically, linear combination of y and x depends on the rank of this pi matrix. So one thing more, here we are basically having two statistics, that is the trace statistics and the max statistics. So and the estimation is done in such a way that for a bivariate model the test will be carried out in two stages. We accept H naught when the series is I1 and not co-integrated, and what is the alternate, that is reject H naught, it means we proceed to stage 1. And here what is the case? H naught gamma is equal to 0, H1 gamma is greater than 0 in the for the trace statistics, and for the maximum eigen H naught, the null hypothesis is gamma is equal to 0, and here H1 gamma is equal to 1. So there is a bit of a difference between trace statistics hypothesis testing and max eigenvalue hypothesis testing. So once this is done, then we move on to the next stage, that is here H0 or the null hypothesis for the case of traces is less than or equal to 1, and H1 gamma is equal to 2. Whereas for the max, again here it is the same, H naught gamma is less than or equal to 1, H1 gamma is equal to 2. And here if we accept H0, then series is I1 and co-integrated, and if we reject H0 over here, the series are I0. So there are two tests to measure the co-integration, trace statistics and maximum eigen statistics. The null hypothesis differs very slightly from these two. Rejecting the null hypothesis by comparing the test statistics is done by the values, special values calculated by or given by Johansen. Now a small note on eigenvalue. See, eigenvalue is also referred to as the characteristic value or the latent root. Eigenvalue is basically the scalar that is used to transform the eigenvector. So like Ax is equal to lambda x. So here the number of scalar values lambda is an eigenvalue of A. If Ax is equal to say lambda x, so the number or scalar value lambda is an eigenvalue of A. We will say we take a very simple example in order to give you a feel of eigenvalue. So suppose we have a 2 by 2 matrix, 0, the first row is 0 minus 2 and the second row is 0 and 4. So using the characteristic equation, we have the identity equation, first row I0, second row 0 1. So what we do in the matrix A minus lambda I is your identity matrix, and we see we equate it with 0. So we take this 0 minus 2 0 4 minus lambda identity matrix, this is equal to 0. So 0 minus 2 0 4, this lambda we take inside, so in place of 1 we write lambda 0 it is 0 0, and lambda 1 it is again lambda. Now we do minus, so 0 minus lambda we get minus lambda, minus 2 minus 0 we get minus 2, 0 and 0 we get 0, 4 minus lambda we get 4 minus lambda is equal to 0. Now here we take, so we do the cross multiplication, so minus lambda multiplied by 4 minus lambda minus 2 multiplied by 0, so this becomes 0. So what we are left, we can write it like this. This cancels out, minus 4 lambda plus lambda square is equal to 0. This we can further algebraically manipulate and write lambda multiplied by lambda minus 4 is equal to 0. So we get one value of lambda as 0 and the other value of lambda is equal to 4. So the two eigenvalues of the given matrix are lambda is 0 and lambda is equal to 4. With this we come to an end on the discussion on Johansen cointegration. Hope the lecture was clear to you. Thank you.